So welcome to our control system design laboratory, and the aims really of the experiment are to investigate PID controller tuning, to have a go at working out a transfer function for a real system, and then using that transfer function and Simulink, a simulation package, to actually tune up the PID controller in simulation and then compare the simulation results with the real results that we've got from our PID controller tuning. And the overall objectives are to control the process trainer, which is this little system down here, which I'll describe in a moment, using a variety of feedback controllers. So the feedback controller that is set up with the following format: standard feedback control system. Here's the process we're controlling. Here's a controller. Here's some sensor. Here's a desired value, and here's an error signal. So this is our overall control system that we have. The actual system we've got is a heating system, so this is a heat energy going in here, gets heated up, you get a temperature out here that's measured by a thermistor bead, which gives you the temperature here. We've got a desired value for the temperature error signal, which then drives the controller. The controller itself is therefore error actuated, so V is the set point and Y is the output, and the control output is given by the proportional gain times error plus the integral gain times the integral of error plus the derivative gain times the rate of change of error. So that's where this term PID comes from: proportional, integral and derivative, and we have three numbers to choose: Kp, Ki and Kd. So this is how it looks in terms of a block diagram. We've got Kp this way, Ki that way and Kd that way, and then they get added together to form the control signal, which then controls the system. And we're going to look at the first part at PID controller tuning to understand how the PID controller works, and the best way to do that is to look at the individual components first and then to add them together. So in the first part, we're going to look at proportional control on its own, so that's Kp with Ki as 0 and Kd as 0. Then integral control with change the Ki but with Kp and Kd set to 0. Derivative control, change the Kd with Kp and Ki set to 0. Then look at proportional plus integral control, where we have Kp and Ki. And in part 5, we can look at proportional plus integral plus derivative control. And the first thing we're going to do, therefore, is look at... Okay, so here's our experimental setup, and it comprises of a long tube here with the heater inserted in here and a little fan here, like sort of fan you'd have in your computer to cool it down. So the fan blows air down here, heats the air up, and we can measure the temperature of the air with a little thermocouple here. If I take this thermocouple out, you'll see it goes completely wrong. If I put it back in, it starts to measure and behave itself again. So here's our little setup. We've also got a computer screen to display what's going on. Now the computer screen has three signals on. The red signal is the set point, that's where we'd like the temperature to be. The green signal is the actual temperature down here, so that's the actual temperature in the rig. And the blue signal is how much heat you're putting into the heater. So there's a few things going on there. Now in order to change the controller, we have a little keyboard down here. And so if I press K on the keyboard, I can select controller gains. So as I choose my different controller gains, I'll get different performances from my control system. So for instance, if I chose, let's say 0.8 and 0 and 0, then this is proportional control. I'll get a certain type of performance here. So this one's not really doing the job for us here. It's not following the red line, which is what we'd like it to do. If we got some other controller, let's say 0, 90, not going to be very good. This is integral control only, so let's have a look what this one does. This one's a bit It's got a bit of overshoot this time, a little bit of undershoot, but notice now this time there's no difference between the two, which is interesting. We change the control again, say we choose 0.9, 1, and let's say 0.4. So just some random numbers now in the controller. We'll notice we'll get a different response. So this time we've got all sorts of weird things going here. So you can see if you choose your controller badly, you can get quite a bad response out of your control system. So the aim of the lab really is to understand what proportional control does, what integral control does, what derivative control does, and how to mix the three together to give you a nice transient response here. So we're hoping that by the end of the lab you'll be able to know how to choose the PID control gains to get a nice response here. So let's see what we might think of a nice response. So if I chose, for instance, 0.6, 0.8 and 0, that's a proportional plus integral controller now, and hopefully this is looking like quite a nice response now. So this is a good, what we might call PI control system design. That shows you a good one. If we chose another one, let's say PID 0.9, 0.9, 0.2. This is a PID design. It's a little bit, maybe a little bit faster than the PI. It's maybe not such quite good on that. Let's try 0.9, 0.9, 0.1. So we have a little bit faster the PID, and that's an example of a fairly well tuned PID controller. So the idea behind the experiment really is so you can know how to play with these controllers to get these types of responses from a given control system. And we're going to do it in a variety of different ways. We'll be looking at tuning it manually and adjusting the gains. We're also going to be looking at modelling the system and using those get models in Simulink to choose the gains. So there's a whole range of different ways we can look at controlling or designing these PID controllers, and that's what we're going to do in this experiment. Proportional control. So proportional control now, we have an error signal and the output is proportional to the error. And we're now going to look at some experimental results of changing the proportional gain on a control system to see what the overall effect on the performance of the control system is. Right, so here we have the closed loop step response with a gain, proportional gain of 0.4. Just to have a look at what's going on here. The red line, let me just wait for it to come back on. The red line is the set point and the green line is the output, and the blue line is the amount of power going to the heater. So this is a proportional gain of 0.4, and this distance here from the red line to the green line is called the steady state error. So this distance now here, this is the steady state error. Now what we should notice is as you increase the proportional gain, the steady state error reduces, but it also becomes more oscillatory. So if we change the gain now, so I'm going to change the gain to 0.8, putting my Ki and Kd as 0, and this now is the proportional control with a gain of 0.8. So notice now the steady state error, that's this distance here, is a bit smaller. Just look on it, but this time it's a bit more oscillatory. So it's improved on the previous response. So if we now change the gain again to say 1.200, this has now got a bigger proportional gain at 1.2, and this time as we increase the gain, it becomes more oscillatory, and this steady state error, that's this distance here, is going down all the time. So this is a good effect of increasing the gain, but this is not such a good effect here, this big overshoot. So if we increase the gain again to 1.6, no proportion, no integral, no derivative, so this has got quite a big gain in now. We now get even a bigger overshoot, and it's now become too oscillatory for a control system. The steady state error has reduced, but at 1.6 now, this is too oscillatory. If we keep the gain going a bit more, up to, let's say 2, then now what will happen is it'll start to exhibit what's called a marginally stable response. This is where it basically oscillates like a sine wave. So this is a marginally stable response, and in this particular case we can also call it like a limit cycle. And this is where the control system is not very good at all. So if we overcook the gain, that's at 2, then we're going to get this type of not very good response occurring. The actual system we've got here can't go unstable because of a limit on the heater values. If it was had a very big heater on it, when it went unstable, the heater would probably melt down. So we can't have that because it's a piece of laboratory equipment. So in this particular case, it's limited the maximum heat level to stop the heater from burning out. So if we go back to a gain K, let's say 1. 1 is not a special number, just chance for this process. But with a gain of 1, we're probably getting our best type of response. So our steady state error is about 1/3 of the output. It's not too oscillatory. Maybe 1.2 is better. 1.200. This might be probably, if we were just having proportional on its own, this is probably what we might go for. It's a little bit oscillatory, but it's also got fairly sort of the smallest steady state error that we can get away with without making this too oscillatory. So that's our proportional controller. What we're going to do next is move on to integral control. Right, so in the second test, we're going to look at integral control. So in this case, the controller is given by Ki times the integral of error. And then we can adjust the Ki and see how the control system behaves as we change the integral controller on its own as a standard integral only control system. Right, so this time we're going to try integral only control. So we're going to put Kp as 0, and we're going to put this as, say, 0.2, Ki as 0.2, Kd as 0. So this is integral only control now, and here we go. And this time the control action is quite slow, but notice there's no steady state error. So the distance up here now, there's no error there, which is an interesting feature of integral control. But there's a response. Let's just have a look at that response again. It's fairly slow. Notice it's quite slow. It's not a fast response. So we could put a bit more Ki in now. So we could go for 0.4, say 0. So now we've doubled the integral control. So the interesting thing about integral control is it doesn't have any steady state error. So this is what looks like quite a nice control system. It's following the set point quite nicely. If we increase the gain further, so it's no proportional, go for 0.6 this time, and 0. So but as we increase the integral, what can happen is it can start to oscillate a bit. So now we've got a bit of overshoot and a bit of undershoot, or not much undershoot at all. So at 0.6 now, it's faster. As we're increasing the gain, it's getting faster, but we're also getting a bit of overshoot now. So we go up to 0.800. So we're increasing the integral gain and seeing what happens. So this time, I've probably probably done something wrong there. I've put in proportional instead, so that wasn't very clever. That's 0.80. So here we go, with the right numbers in now. So this integral control with 0.8. So this time get even more overshoot and a little bit of undershoot this time, but it still has this sort of zero steady state error. So the error down here is going to 0. So if we go to k, so I've been what I'm doing now, 0 proportional, 1 integral, and 0 derivative. So this time it's going to be even faster, but more overshoot and more undershoot. So trouble now is become almost like it's faster, but too much oscillation. And if we go for a bigger gain here, say 1.2, no, that's not good, is it? 0, 1.20. So now we've got Ki set quite high. So this time we're going to get it's still stable, but that overshoot is growing. So if we change K again to 0, let's say 1.6. No, that's no good. I'll have to come out of this. 0, 0, press K again, so I put the wrong numbers. So it's going to be 0, 1.60. So this has got quite a bit of integral control in now. So now it's almost gone into like a limit cycle, like the previous one. So this is exhibiting now not very good behaviour at all, characterised by this signal here forming like a limit cycle. So in that particular case, we would say that this had gone marginally stable. So the integral control has gone marginally stable about this value. So we'll have to reduce our integral control to get back to our nice controller. So go to 0. So we try 1 again, 0, just to see what we think might be our best controller. This one doesn't look too good, does it? So 1 is definitely too much. Should go to 0. So should we try 0.70? So this has got about a 20% overshoot. That's probably about the best we could achieve. So that would be probably our best integral only controller. So that's integral control. What we're going to do next is move on to derivative control. In the third part, we're going to look at derivative control. This one looks at the rate of change of the error. So the output is proportional to some gain, Kd, d for derivative, times the rate of change of the error. So this is then called derivative control. Okay, so in this case, we're looking at derivative control. So no proportional, no integral, and let's say go for 1 derivative. And let's see what happens. So notice now, it's not really doing much at all. The signal, in fact, it's like quite oscillatory. Notice this signal down here is very, very bumpy. So the system switching itself on and off, and the derivative control really, on its own, isn't very effective at all as a controller. Let's just try a different value. Let's go for 0, 0. Let's say go for 0.4, slightly less Kd. But notice that derivative control on its own just doesn't really do much for us. So in this case, hasn't done a thing at all. So derivative control on its own, let's try one more, shall we? K, so that's going to be 0, 0. Let's try 0.8, shall we? So looking at this, what's going on here, so it's not really effective at all, the derivative. Doesn't have any real influence on control, but it does have influence on if used with another controller. So we're going to look at that next. So having looked at the controllers on their own, we can now look at combinations of them. So a couple of combinations might be P and I, another one might be PI and D. So in this case, we'd have 2 parameters to choose. In this case, 3 parameters. Usually as the controller gets more complicated, you can get better performance out of it. And the type of thing we're looking for in terms of performance is that the transient response can be as fast as it possibly can here, fast rise time, but very little overshoot and very little undershoot. So it comes up, holds the line, gives us a nice transient response. This one with a bit of, this has got too much overshoot, too much undershoot. This one's a bit slow coming up here. So we're looking for to minimize really the error signal here, minimize the area by coming up quick as you can, minimum overshoot, hold the line and just track the desired set point all the time. That would be a good, well-tuned control system. So what we're looking at is at tuning up the PI and then at looking at tuning up the PID controller. Right, so now we're going to try PI control. That's a bit of proportional plus a bit of integral. And so I thought we'll start off with 0.5 and 0.5 and no derivative. So this is more complicated now because you're in a two-dimensional space. Now this one's isn't too bad really. It's a little bit low here, so but it's quite good along here. So 0.5 and 0.5 looks half interesting. Let's try another one. So we try 1 and 1. Just see what that one does. So we put the gains up now to expect to be a bit faster. So this time we've got a bit more overshoot here, a bit of undershoot, but still quite good along here. So you can see that 1 and 1 is too big, and 0.5 and 0.5 is a bit low. So if we went for gains of say 0.75 and 0.75 and 0, so we're sort of honing in now on what might be our design. This one's a little bit overshoot, quite a bit of undershoot there. A lot of undershoot is an indicator that Ki is too low, and maybe this little bit of overshoot is indicating Kp is a bit high. So if we go K, so we're just going to shave a bit off this. So let's go for say 0.6 and just a little bit more here. So go for 0.8 and 0. So now adjusting them to be slightly different, and we now get something that looks quite interesting. It's gone up here quite fast, very little overshoot, very little undershoot, and it's going on there. And that we consider that to be a well-tuned PI control system. So let's have a look at that working again. So this is a well-tuned PI control system now. It's showing very little overshoot, very little undershoot, and good set point tracking along there as we're going along. So that's our PI control system, but there's a bit more fiddling to get it to. So now we're going to look at PID control. That's choosing all 3 parameters. We're going to start off with a solution we had a minute ago, which is Kp as 1, Ki as 1 and Kd as 0. So remember, this one wasn't that good. It was a little bit oscillatory. So this one's got quite a bit of overshoot here and quite a bit of undershoot there, but the rest of it is quite good. Now if we can put derivative in to get rid of this overshoot and undershoot. So that's the main trick of derivative. So if we stick to K as 1, Ki as 1, but this is 0.1 now. We don't want too much derivative. Too much derivative will amplify noise. So here we go. This is our PID controller now. And notice now it's significantly reduced the overshoot and undershoot here, but it's a little bit noisy, so it can exhibit slightly strange properties, but you can see that big overshoot and undershoot has now gone with the PID control. Let's just try some different values for D for you to see the effect of it. So we stick to 1 and 1 and type 0.05, so we've halved the derivative. So this is halving derivative control now. So this time it has reduced the overshoot and undershoot, but not as much, so we've got a bit more overshoot and undershoot here. Let's go back to 0.1 and 0.1 as well to see that. So K, so go 1, 1, go back to 0.1. We'll notice that that overshoot has significant and undershoot has significant reduced. So obviously 0.1 looks quite promising. If we go for K as 1, 1 and 0.2, that's doubling the derivative from what we had before. Derivative is always, you can use a bit of it but not much. Notice now with a little bit more derivative, this signal here is like quite noisy, and we've introduced now some sort of higher frequency oscillation into our system. If we keep on increasing that derivative gain 1, 1 and say 0.4, this will get worse. So a little bit of derivative, so you can see now it's gone quite sort of into some sort of high frequency extra oscillation in there due to the derivative control. So it's not a win-win situation with derivative. So we go back to 1, 1 and 0.1. This is probably our best derivative controller. So here we go. So this is a good little controller, this, isn't it? Notice it's coming up here in about where that dotted line is there, that's quite fast for your PID. Let's just compare that, shall we, back to our PI. Remember our PI, it was 0.6 and 0.8 and 0, so this is our fairly well tuned PI controller. Let's just see where that one comes up. That one's a little bit slower here, so it's a bit slower. The other one's up there, this is a bit slower. So your PID is about 10% faster than your PI. Let's just go back to that again. So we could have, say, 1, 1 and 0.1. So it's always worth considering, if you really want to squeeze performance out of your control system, then increasing your gains and putting a bit of derivative in. But if you put too much in, it'll amplify noise and it'll go bad on you. So that's our PID tuning now. So that concludes our PI, and PID. Right, so this next section is based on model-based PID tuning, and it's another way to tune a PID controller. And this time, because it's model-based, we're going to have to work out a transfer function for the system. Then we're going to use the transfer function and a simulation package and a closed loop control system so as we can tune our PID controller. Now this can be useful because when you first go onto a control system, you don't know what controller gains to choose. So if you chose the wrong values, you could make it go unstable. If it were unstable, it could blow up, in which case you'd be looking a bit red-faced. So to avoid these type of problems, we can model the system as a transfer function, then use Simulink to model the closed loop system, and then from that we can choose some appropriate gains without taking the risk of making the real system go unstable. Now in this particular case, every system has its own particular transfer function, and working out the transfer function can be at times tricky. But for this particular system, we know it can be modelled by the following transfer function here. It's a first order system with something called a pure time delay. So we've not met one of these before, but a pure time delay is something that when it happens, it takes a finite time before it comes out. So, and this, the time it takes to come out is called the time delay. So it's a bit like an escalator. So you go onto the escalator, and then you have to wait all the way until you get to the top of the escalator before you come off. And TD, the time it takes to travel up the escalator. So that's the TD. K is our standard steady state gain. TP is our time constant. So in this model, we have three parameters: steady state gain, the time constant, and the time delay. And if we looked at an open loop step response to the system, it would look something like this. So we put a step in at the input, and this is what we'd expect to get to the output. So this is the pure time delay effect here. So nothing happens for a certain length of time, and then it zooms up to a value K. And at 63% of the value, you get the time constant. So here's an example here, a little transfer function, 10, 3s plus 1, e to the minus 2s, so this would be 2 seconds here. So it takes 2 seconds before anything happened. The k is 10, so it's going to go to 10. So from there to there is 10. And if we take 0.63, which is 0.6 through 10 is 6.3, so go to a line from where it starts to go up to this point here, that gives us TP. That should have been TP there, shouldn't it? So that's a way of getting at our K, TP and TD. And if you remember back to our little live demo that we've got, we've got a step, we can get a step response look something like this, and then we could potentially measure K, we could potentially measure TD, take 63% of K, and we can measure TP. So that'd be one way to do it. We could do this by measuring values off the screen, which is sort of acceptable, but it's not very accurate. So what we've done in this particular case is the blue line and the green line have been stored. So we've run the experiment, and we've stored this data into a data structure, put it on USB pen, and then made it available for you to load in to MATLAB. So then you can have the real data very accurately in front of you to process. So the data now will be on Blackboard, and it's called Lab Data 2020. So you access this data, download it, and I'd recommend you put it on like a USB pen. Now the USB pen, when you put it in, will have a direct file like an E or a G or something in there. You need to know what that is, and then if you type in at the MATLAB command prompt that's in MATLAB, load single quote, load open round bracket single quote, then this is the directory it's in, and then this is the name of it with a single quote 20. So just type in that. You're gonna just change that letter there basically if you've got a USB pen, and that'll be whatever letter is given to your pen drive, and that will have the effect of loading the data from the real-time test into MATLAB. So that gives us a way of getting the data into MATLAB, and then once you've got into MATLAB, you're then going to load in a second program into Simulink. So we're going to boot up Simulink. I'm going to show you how to do this in another little part of the video in about 5 minutes time, so don't worry too much about it at the moment, because I'm going to take you step by step doing this. So load now the Simulink Modeling 2020, and this little program here, this simulation will come up, and this has got 5 parameters for you to choose really. Now there's 200 I've met before, is U offset and Y offset. If we look at our system here, it doesn't actually start at 0. Now when we model systems, the theory really works on the basis that they are locally linearized and that they start from 0. So this one doesn't start at 0 either here or here. It starts about 800, and this starts at about 1400. So we'll have to subtract now these offsets from the data to make them start at 0, and that's what this U offset and Y offset does. And then having offset them back to 0, we can then choose KP and KD or K, TP and TD in our transfer function here. And the way we're going to do that is we're going to have a little transfer function which we're going to choose the parameters for here, and this is our real data coming down here. So this signal here is this signal here. This is the real data, and then we've got this input signal here, and the input signal is fed into the model. So if we choose the model correctly, the output from the model and the real data will be identical. So what we're going to do is we're going to adjust K and TP and TD until these 2 bits of data look exactly the same, and then we know then that we've got ourselves the correct transfer function. So let's have a look. Let's have a look at a recap of what we're doing. So this is the simulation program. You've loaded the data now. I've called it Y data and U data into MATLAB. So Y data is the real output data from the rig, and that comes down here and is just displayed on the screen. But we've also got a little offset to put on it to make sure it starts at 0 rather than starts at 4000. So 1400. So this is going to be, say, you set that at 1400 and it'll subtract that from it to start it off at 0. Then this is U data is the blue signal, the one that started at 800 and went up to 1800. So that's going to be offset by 800 to start at 0. And then you're going to choose K, TP, and inside that box there is the time delay TD. And you're going to choose these three numbers now. So it's the two outputs here, when you look at them, look exactly the same. So this is what typical output when you've done it correctly. And the two graphs sit on top of each other. So you've got two graphs there, one of the real output and one of the model. And when they sit on top of each other, you've got a good idea that you've got the right numbers for K, TP and for TD. So how do you do it? Well, it's a 5-step process. First of all, correct the input data offset, then the output data offset, then identify the steady state gain, then identify the time delay, and finally identify the time constant. If you do them in this order, it's quite easy. If you do them in any other order, it's quite hard. So let's have a look what we do first of all. The first thing we do is we look at the output coming from the U data here, the signal here, and we want that to be 0. So if we put a scope on at the moment, it starts off at about 800 and goes up to 1800. So we want to start at 0, so I'm going to plus or minus here, put 800 in there, and it'll bring this down to 0. So the signal here should look like this, and the signal here will look like, and we've now got a 0 start on our input. We can do the same for the output. The output starts at some value here, so that's the value, so we can then subtract a certain number from it until it starts at 0. So you just adjust that number until this goes to 0. So that's going to be specific to the data, which could be different from minute to minute, day to day. So these numbers, that number there, depending on what data I send you, will be adjustable by you. But the main trick is make sure it starts off at 0 there. You could put a little scope there, stick one of those on there, and you can see that value. So once you've done that, we've now got this value here coming at 0 and that value there starting off at 0. So when we get the graphs now, they start off at 0. So next thing we're going to do now is you're going to have to, the MATLAB won't like it unless it knows the numbers. So you're going to have to guess a value for K, TP and TD. So I suggest you choose K as 1, TP as 1 and TD as 1 at the start, just so it's got some numbers in. So double click on these, set the numbers up as 1 and then run the simulation. Now what will happen is probably your K might be too big or too low. So the one we're going to play about with now, first of all, is K. And we're going to, there'll be the signal here will be, this will be the real data. And the other, either if the K is too low, your output will be down here. That's this signal here, will be down there. Or if it's too big, it'll be up here. And this, the red line is what's coming down here. This is the real data, that's the red line. So you adjust now K until, if it was like, say, this one, you'd make K a bit smaller and it would come down until it sat on top. Or if it was this one, K was a bit low, make it a bit bigger until it sat on top. And that would give you then the right value for K. So when you've done that, the K value now will be correct. So it'll be the right value along here. Next thing we go for is TD. This is the time delay inside this box. Now, if TD is too small, it'll start coming up too early. If TD is too big, it'll start coming up too late. So adjust TD now until it starts coming up at the right time. So this is 2D too big, this is 2D TD too small. And you can just adjust it, make it a bit bigger or a bit smaller until it starts off at exactly the right point, the same as the real data. So then you've got the TD correct and the K correct. So having got the TD correct now and the K correct, the last thing to change is the time constant. Now if your time constant is too big, it's going to be small. If your time constant is too small, it's going to be fast. So then adjust, this is TP too small, so let's make it a bit bigger. I'll slow it down. This one, TP is too big, so it's too slow. Make it a bit smaller and you can speed it up. And you can push that way or that way until you get exactly the same graph. So when you've done that, you'll then get the two lines sitting on top of each other, and you'll know what KTP and TD is. And that's like using the real data to model your transfer function to pick up your parameters of your transfer function. So once you've got those, then you've then got yourself a transfer function. Now what I'll do next is I'll go through that with you step by step using the MATLAB program, so as you can see exactly how to do it. Right, so now we've loaded up MATLAB, and the first thing I'm going to do is load in the data. Now you need to know where your data is, so if we go on to I've actually put it on my USB drive and it's labeled it E, and it's sitting down here. It's lab data 2020 in E. So load the data from Blackboard, stick it on a pen drive, put it at top level, then you haven't got to put a path in here to get the path wrong. So that'll give you an easy way of getting your data in. And go into MATLAB and type in load, open round bracket, yeah, that's load, open round bracket, single quote, E colon lab data underscore 2020, and it should then load in. Mine didn't work because I didn't type in the little quote at the end, so you've got to put a little quote at the end. So put that little quote in there, goes all nice and purple, and it loads the data in. So once you've got that going, we can then load in our Simulink. So we go onto Simulink here, double click on Simulink, and then Simulink will start up. So if I double click on this, Simulink starts up, and then I've actually loaded this program in before, so you then load in then this Simulink Modeling 2020. So load in that program, and here we have the program here now. So this is the one. So Y data and U data now is in. Now these bits are in red because it doesn't know what the numbers are. So we're going to have to choose these now. So, but this is the KTPTD. These are the two offsets. Now it won't run as it is until it's got some numbers in these boxes. So double click on this and just choose now. I suggest 1 for everything for a start. Double click on that one, set that as say 1 as well, and then your offset, your Y data offset, start that off as say 1000, and your U offset, you probably know what that is, it's 800. So we now got some numbers in this, and we can run the simulation. So run the simulation, click on the run button, and wait until it comes up with a funny little noise. There you go, you get the funny little noise. Now have a look here first of all. We click on there. This with a bit of luck, a bit slow. This should start off at 0. It's not starting. Mine's starting off at about 100. So if you look at this signal here, it's actually starting off at 900. So I got the numbers wrong. So that should be 900. So you'd look at the data here, see what that value is there. It's 900, and put that number in here. You don't always have to do this with real data because it'll have some sort of offset on it. So now if we run again, you have to run it before it'll have any effect. If we then look at this signal here, it's now starting off at 0, which is what we have to have. That signal starting off at 0. If we look at this signal here now, it's starting off again. It's not starting off at 0. It's a little bit higher than that. So if we go back to here, have a look here, starting off at about 1080 or something like that. So this should actually be 1080, 1080, and we click on OK on that, and then run. We should then see this signal here as more or less starting off at 0. So that's the first thing we've done. We've set the two offsets. Now if we look at the output here now, we'll notice we'll get a model output and the real output. So let's have a look at that. So now we've got two signals here. So we've got the real output here and the model output here. So they're not matching. Because they're not matching, the model's not right. So we're going to have to make this go up a bit this way, and we're going to have to make this go down that way. And we're going to have to probably, this doesn't look that much far off, but need a bit of adjusting as well. So the first thing to adjust K. So K needs to go up, and probably needs to go up by about 20% or so. So if I choose my K now, and my K is the number on the top, make it about 20% bigger, make it 1.2. And then run. Have another look. Oh, I've got it. That's cheating, isn't it? But it's got it spot on there. So if I'd chosen something a bit too big, say I'd made a mistake, I'd chosen 1.4 for instance, and run it again, it's now going to come up too high. So it's now come up too high. So we know now because it was 1.2. 1.2. So when we run that, we now know that we've got the value for the K, the steady state gain, correct. Now looking over here now, this is the time delay. The step comes in at 1. So you can see the time delay in the model is a bit too big, so we need to reduce it. So let's reduce it now by clicking on this button here, and we'll make this say 0.5, and then run it again. And it's better now, but it's still a bit big, isn't it? Still a bit big, so I could do it going down a bit more. So let's try it at 0.4. Run it again. Sorry about the. Have a quick look at this. So that's quite good, isn't it? It's more or less starting exactly the same place now. Now the yellow line is a bit slow, so that means the time constant, this is too big. So we need to push the time constant, make it a bit smaller to push the line upwards. So if we go back now to the time constant, and the time constant is the number in here. So say I have it as 0.5 for instance. So let's make it smaller. And this time it's too fast. So 0.5 was too big. So go back to here. So let's try 0.7, shall we? And then run that. And then we've got them more or less fitting on top of each other now. So we now know that the data coming off the rig and the data coming off the real system are a good fit. And we know now that K is 1.2, TP 0.7, and TD is 0.4. So now we've been able to model the system now to use later on as a closed loop simulation. You could do a screen dump of this using print screen to get that off, and then if you double click on this to get your graphs, if you do file, copy to clipboard, you can then copy that graph, and if you open up Word or something like that, I'm just going to open Word, but I should have had Word opened up already, but I haven't. If you open up Word, you can then paste your diagram into Word, and you can adjust its size like that. If you want to get this thing into a thing, I suggest print screen. So press print screen, and then go back to your Word document, and do paste, then click on that, and then do picture format, crop, and then just crop it up. I love this command. It's really great for nicking stuff from anybody. So you can nick it from MATLAB and make it like that, and bingo, you've got a lovely little block diagram that you can have any size you like. So then that's how you can get your data or your graphs and things from MATLAB. into Word to write your lab report. So that's how we're going to go about now. We choose these two numbers first, then we choose the K, then we choose the TD, then we choose the TP. That's your modelling technique then, because what you've got is now you've got real data coming into a model. The output data from that real data has gone into the real model to give this real output data. You're comparing the two. When they both look more or less the same, you're pretty assured that your model is good. So that's our modelling technique. Right, so once you've now got your transfer function, your K, your TP and your TD, you can set up now this little closed loop feedback control system. This is the proportional controller here. This is the integral. This is the derivative. The derivative is done through a d by du. That's a derivative term. That 1 over s is integrator. And so now we've got a little simulation now which we can run. And so what we want to do is go through now what we did in the first half of the lab on the tuning, which is look at just have it under proportional control, have it just under integral control, and just derivative control, PI control and PID control, and get a range of different gains in here, which you can then compare with your practical results, which I did for you in the first half of this thing. So what you could do is you could take screenshots from the video of some of my results, and then you could compare and contrast them with your results to come up with a view of how close my results are to yours. So then you can do that then for these 5 cases, and that's for you to do as an extra little part of the assignment, to look at tuning controllers on the theoretical front and then comparing them with the ones that we might have obtained practically. So just to recap then, these are the ones you're going to do, the 5 different ones. Just as an example of what we've done, remember in the practical sessions we had about 0.6 and 0.8 and 0 was like a PID controller. So if we chose those numbers, if I double click on these boxes, set the numbers up, I can then run the simulation, and this is the response I'm expecting to get from my simulation, which we can see isn't that far off what we got in our practical results. If we chose some other numbers, let's say maybe this was 1 and this was 1 as well, and that was 0, we get some different result now. So it's now more oscillatory, as we might expect by increasing the controller gains. I think another one we got was 0.9 in here, 0.9, and this one is 0.9, and this one as 0.1. That was one of our other controllers that we had, 0.9, 0.91, 0.1. Run that one. Again, we're getting quite a slightly faster response here. So it's indicating there's a reasonable correlation between our model and our theoretical results and our practical results. It's not always going to be the case, but you can see that in these particular 2 cases it wasn't too far off. Okay, so we're now down to, we've concluded all of the experiment now. So I want you to think about writing this up, and as part of the write-up we need to think of the discussion. So explain what a PID controller is, how do the different parts, the P and the I and the D, work, how do you tune them, what is a transfer function, how do you identify a transfer function from real data, and how you can use Simulink to tune a PID controller, maybe what the advantages and disadvantages of doing that are, and then in conclusions, how well your aims were met. And that will give us the discussion and the conclusion in the final section of your report.